Welcome again to the NPTEL course on storage systems. In the previous class, we discussed some basics and we were looking at some aspects relating to naming and storing. Okay. A storage system, these are the two important things that it does. One is how to name something and how to store it, and later we have to retrieve, of course. When I mean storing, I am also meaning storing and retrieving, both I am talking about. Okay. So, as I mentioned last time, naming is can be quite complicated. It is not that simple a thing. Okay. And that also you will see in real life. For example, you have, if you are a student, right, you have a regular name, you might have a roll number as a correspondence. Okay. And how the roll number is decided might be depending on some structure, right. And if you think about it a bit more carefully, that is why the Indian government wants something called UID. What is UID? Unique ID. They believe that somehow it helps in reducing lots of complications that are there in our society with respect to getting benefits, etc. Right. There is some, that naming somehow is supposed to help a lot. And you will also see this also if you study, anybody who has studied theory of computation, right, you notice that the naming is an important part. Why do I say this? Has anybody heard of something called lambda calculus? Anybody has heard of it? You will see that lambda calculus has got only 3 rules, something called alpha rule, beta rule and eta rule. Alpha rule is about naming, what is called, it is a way of, there is something called alpha rule which basically talks about which variables have to be, are being discussed, okay. That is all it is, and how to do renaming, okay. And the beta rule is all about how to do function application, okay. The eta rule is some, I do not want to get into it, but it is something, it turns out that having these 2 major rules, alpha and beta rules, you can do everything a Turing machine can do. Okay. Anything and everything. So, hidden between this simple sounding thing called naming and storing lies the complete power of a Turing machine. It might come as a surprise to you. If you study lambda calculus, you will find it. Okay. So, that is the reason why the storage system not only does seemingly simple things like naming, storing, it also does a lot of computation. That is what we were talking last time. It can involve significant computation. It is compression, encryption, coding, deduplication, etc. So, again we will just quickly look at this. What is compression? Compression is a way of saying, if I see something repeated, some segment of something repeatedly coming in, instead of repeating it every time, I use a pointer or a much shorter way of referring to that, okay. And basically I am trying to reduce the space that is taken of it. In encryption, what am I doing? There are varieties of possibilities. I can use what is called, there are simpler schemes and there are slightly more complicated schemes. For example, if you use something like AES, right, it uses just a single key, whereas there are other systems which use 2 keys, for example, private and public keys for a different type of cryptography. And nowadays we have something called identity based encryption also, IBE, that also is there. Okay. There are varieties of systems also here. Okay. Now for each of those things, different kind of solutions have to be adopted, because fundamentally the keys have to be stored and these keys have to be made available in the future whenever you want to decrypt it. So there is the fact that you use encryption does not solve a storage problem. You have to also figure out how to store and retrieve the keys. So there is a recursion problem here. Similarly, coding also is there. It turns out encryption is a form of coding. You use encryption or the term encryption when you want to say it cannot be broken easily by anybody else unless you have the keys. Coding is a simple way of saying that I am transforming the data into some other variety for reasons of convenience, for reasons of if I lose one piece I should be able to retrieve the information back in some other way. I'm not interested in secrecy or unbreakability of the code. Okay. So, for example, you have things like RAID 1 or RAID 5. What is RAID 1? You typically keep another copy, okay, just a copy. So, means if your data is X, it's going to be 2X, the total amount of space that required. Or you can have what is called RAID 5. What you do is, you have data something. What you do is, you store one segment of the data in one disk, second data on second disk, third disk, fourth disk. On the fifth disk, you do XOR of all it and keep it there, of X1, X2, X3, X4. Because you're doing XOR, which is a low cost operation, XORing is not that complicated, okay, exclusive OR. So, if any one of them is lost, one of the disks breaks down, if I XOR the rest of them, I get what has been the disk that has been lost. So, this is an example of coding which is not cryptographic quality. It is a trivial thing, anybody can do it. You don't need any keys etc. for it. Okay. So, this is widely used, and you will see in many PCs nowadays you get RAID as part of your system. Actually, some laptops already have RAID systems on it. That means they have 2 copies of data, 2 disks, and then they do this. Why do you need this kind of coding? Because the disk can fail. Okay. This is an example of failure management. Okay. And this is quite critical for very large scale systems. If you look at Google, they have data in the region of tens of petabytes or more, and they cannot afford to lose the data. Okay. So, they usually use 3 copies. Every single piece of data is actually typically copied, 2 extra copies are made, and they often can be done distributed. One piece of it is staying in Europe, one is in Asia, one it is in US for example. Okay. And so, this is a widespread thing, and the reason why you need to do it also is because errors cannot be eliminated. One is disk failure, another is disk may not fail, but the medium gets corrupted here and there. Last time we talked about sector errors, and this is not uncommon. Even if you use the best error coding schemes, you will find that there are still uncorrectable errors. For example, in disks they use something called Reed-Solomon coding widely, and for example, for every 512 bits, as much as about 40 to 50 or 60 bits are used to encode that 512 bit, so that even if a burst of errors takes place, for example 4 or 5 bits get lost or even 10 bits get lost, I can still recover the whole thing. Actually, this has been carried to very interesting levels. If you take a CD-ROM for example, you can drill a hole in it somewhere, anywhere, okay, as long as mechanically you don't destroy it in a way which prevents you from putting it inside the CD drive. Okay, you can drill a hole in it, it will still be able to read it, because they use what is called longitudinal and horizontal. I shouldn't say, okay, they are 2-dimensional encoding. Let me not call it longitudinal. They use 2-dimensional encoding. That is, the sectors, you can think of it as sector 1, sector 2, sector 3, sector 4. They do encoding this way, they do encoding this way. Okay. So, they use fairly sophisticated techniques, but in spite of that, you know that CDs cannot be read sometimes. Why does it happen? Not because of the coding problem, it is because you use certain types of dies, and the cheap disks you often find, the dies get spoiled. Okay. They decompose under some sunlight or some light conditions. So, after 1 year or so, they die. You can't do anything with it. Okay. That is why don't ever trust anything valuable on a CD that is bought without knowing where it is coming from. If you are very careful, if you buy the best quality CDs, it may last you for about 5 to 10 years. That is all. Okay. Nobody will guarantee anything more. Okay. Whereas, if you buy the cheapest brand somewhere, right, most likely it will not last for more than 6 to 8, 10 months. Okay. Okay. So, be careful about CDs. Okay. Disks are better because they have been designed for use in let us say business kind of applications. So, you need to make sure it survives that long. So, what I am trying to suggest is the coding is an important part of the disk systems, okay, or storage systems. And that's the reason why if you look at a disk, you will see that it has got a processing power which is approximately that of a, in those days sometime back they used to call it about 20M 400 megahertz processor. That means that if you have a laptop, let's say an atom based processor, let us say 1.6 gigahertz or whatever it is, about 1/4 or even slightly more of the processing power of the laptop is sitting in the disk itself. Okay, it is doing all this Reed-Solomon coding, it is doing buffering, it is doing various kinds of things. Okay, that amount of processing power is sitting there. Again, if you open a disk, you'll see a motherboard there. Not, I shouldn't call it a motherboard, that's a circuit board you'll see. Okay, and that circuit board has got a processor. Okay, so actually you can even go even to a much higher level, deduplication. Okay, what is deduplication? I think I briefly mentioned it last time. The idea is that you tend to have multiple copies of the same thing. I keep forwarding my mail, right? You sent me some mail with an attachment with 507 photographs. I forward it to you, right? And I keep a copy of my sent mail. Right? I might even have so many copies, right? So, or I might, when you are working on a document, you keep modifying it. Let's say there are 3 people working on a document. You make modification, that person makes a modification, I make a modification. So, most of the times I keep modifying different parts of it. If I can figure out how my document different from yours, what is the delta that I have caused, then I can say that I can represent the current version of this as some set of basic parts of it with that small addition made by that person, small addition made by you, and small addition made by me. Okay, that can reduce it quite a bit. That's the reason why many people say nowadays that close to, I think I quoted the figure last time, 90 to 80% of all storage often you hold is often duplicate. Okay, on big enterprise systems, people found this. Okay, so if you can cut it out by 1/10, nothing like it. Okay. So, but I think I mentioned last time there's a problem with deduplication. What is that? That means that every time you get a piece of data, you have to compare it with every other piece of data you have. I'm only talking about 100 petabytes kind of systems. I get one file, I have to check it with a 100 petabyte file system. Okay. How do you do it fast? It's non-trivial. Again, I think all of you by now should notice that this naming and storing is not a trivial thing, because that's one thing we human beings also do a bit. We try to store something in our heads, right? If you think that it is trivial, okay, then we're not, you don't know what all we go through to remember something, right? Because a lot of the complexity of our life is all about trying to remember certain things, right? We forget certain things, sometimes it's just on the tip of our tongue, we can't figure out where it is. There's some complication there, right? It's not a trivial thing, okay? I think we can say that if we find that the brain is one of the most sophisticated systems that has been designed, okay? If it has problems about remembering and storing, it's because of the large numbers of things, okay? You can see a corresponding situation also in large scale storage systems, okay? Things can get corrupted, somebody has to correct it, things can be in multiple pieces, you have to join them together. It might be deduplicated, you have to pick up some piece from there, from here, please and put them together, all kinds of things of that kind will be going on, okay? So, even our brain might be doing some of these things, okay? For example, our brain might be doing some compression. That means that it sometimes stores something with just a pointer, and then you think a bit more about the thing, then you remember more details. Okay, that means you have an initial handle only, rest of it is sitting somewhere, don't know where, okay? And then you keep thinking and thinking, you finally get the thing. And that's why, for example, some of people say hypnosis, right? They say that if you hypnotize it, you can remember things which you cannot otherwise remember in your conscious state. People say this, right? Same thing about, of course, I don't know whether we do encryption, okay? So there are certain kinds of things that we human beings also do, okay? And the same complexity that attends to a storage system is there in our systems also. Okay. And more important thing for us as storage systems is that you always need to keep auxiliary information on an object. That is, it's not necessary just to store the thing. I need to know, I need to keep an index about it. I think one of the big problems we often have is that we kept the thing somewhere but don't know where we kept it, right? So that where we kept it is a critical part. Not only where we kept it, but sometimes you need to know what kind of thing have you kept, right? So, if you don't have some auxiliary information, then you have to go through the whole document again to figure out what it is, right. So, this auxiliary information about an object is basically called a metadata, okay. That is data about data, metadata. Now, you can see that this is already is a treacherous concept. Why? If I say that there is data about data, then I can do recursion. What about data about data about it? That is metadata about metadata about metadata. I can do this, and we have to do it. It has to be done. So, typically we do about 2 or 3 levels of recursion in file storage systems. For example, you have piece of a file, you have inodes, but then somebody has to figure out where the inodes are. Okay. That means you also have to now start thinking about where you kept the thing. Of course, you can even continue further, but typically you go about 3 or 4 levels. More than that is going to be tricky. Okay. So, the reason why this happens is that again for reasons which we discussed earlier. Suppose I have some piece of information kept in 3 places. The data is here, data is here, data is here. I lost this part. Then I need to have information saying that I got 2 copies here and here, right. Now, if this information itself is lost, then all that amazing thing I kept on is also useless, right. I have metadata about where I kept things, but nothing says that I cannot lose this. I can lose the metadata itself. Then I am almost like a lobotomized guy. I don't even know where to start, right. That means that I have to replicate even the metadata. If I replicate the metadata, then again you say, who is going to keep track of where things are? Okay, again you can start thinking, how do you do this? Okay. And these things are extremely challenging problems. There are no obvious solutions. There are practical engineering solutions for all this. Practical engineering solutions. That's the reason why Google File System works. Not because they have solved an impossible problem. There are lots of impossible problems, okay, in this area. The idea is that you solve a problem to the extent it is feasible, so that it does what our job is, what we need to do, that is it. Okay. You do not try to solve impossible problems. Okay. So, a lot of it is about fundamentally there are some delicate issues here. Okay. So, you normally what you do is you want to break the recursion. So, basically you go 2 or 3 levels, and finally there is to be a place where you have to fix it. You say that the root of the information is here, and it will only kept in 2 exactly known places, and it is known. It's like you are on a disk, there is something called master boot record. It is known to be on sector 1 or sector 2, that's it, it is known, okay. And there is no, of course you have to know that it is there in sector 1, sector 2. Where is that information coming from? Is because on the particular level of technology, somebody has, it is widespread knowledge somewhere. And that is one of the kinds of knowledge that gets lost over centuries, right. If you try to remember that the system, suppose I want to carry it across, there is some information on metadata, okay. It may be known commonly now, right. For example, almost everybody knows that we use something called ext2 file system, and it stores the super block in a particular place, okay. Probably super block might be there in sector 3 and sector 4, whatever it is, okay. But that may not be constant across all file systems, but it's known around right now. So, now it is not like, doesn't look like a very critical piece of information. But once you have gone a few decades in the future, okay, this common knowledge will not be there. So, then you have to get that piece of knowledge in a very hard way, okay. It's not going to trivial, okay. I think you must have come across this. One of the reasons why you do all this archaeology, you do all kinds of trying to figure out what happened in the past, is that you have to take these clues from here and there, scattered here and there, because the metadata is lost somewhere. You take these clues and somehow reconstruct the past, okay. That's some kind of detective work, okay. So, so I just wanted to mention that there are, if you think about all this a bit carefully, you will see that some of these things are non-trivial, okay. And for the same reason I mentioned, you have this ability to withstand data loss versus metadata loss. Again, there are different issues here. Some people value data more than metadata. I'll give an example. Suppose you are doing, you have kept your information about your bank account, right? Now what is important? How much money you have is more important, or the pointer which kept where the, how much money you have is important, okay? Many people will say the more important thing is, even the pointer is lost, if someone is able to figure out how much money I have, that's more than enough, right? So basically people will say data is very critical, protect it against all costs, at all costs. Even if the pointer is lost, I'll scan the whole thing, the most laborious fashion imaginable, okay? And hopefully I'll be able to see that my name is somewhere and my account is somewhere there, okay? Some of you might have heard about something called FSCK. What is it? File system check, right? That's basically what it's doing, okay? I'm simplifying it too much, but basically what it's doing is, it's saying that some pointers have been lost, okay? It says that yes, pointers have been lost, things are looking bad, but I still have the data. The disk itself is still luckily readable. Most of the disk is still readable. Some part of the disk is gone, that's why I lost pointers. But most of the disk is still readable. So what am I going to do? I'm going to say I'm going to do the most dumb or the most harrowing thing possible. I'll read every single block, okay? See if the information, what I'm looking for, what is important to me. Can I say that, can I tag that these are all important and somehow create a new index structure, even, what do you say, even though I lost some things, because I'm still valuing the data. So some people will value data much more than metadata. And a good example is, I told you, anybody in the finance section, financial sector, they will value it. Database people will value data more than metadata, okay? Metadata they will say, we'll figure out some way, okay? Because it's valuable stuff, I have to do something about it. The other people will say the opposite. Who are other people? Suppose you are a file system guy, okay? What is your business? You are providing a service to various users. You are on a single system with 105 people using the system. Your your sector died, okay? Something happened to yourself. What is my responsibility? Should I shut down the system or say, I don't mind that you lost something, but there are 104 other people, I'll still serve them. What is the calculation the file system should make? It will say that something is wrong with this stuff, I'm sorry, I don't know what to do with it, I'll proceed with other guys. That's what a file system does, okay? So the thing is, what is the file system doing? It's saying the following: you have not told me what is important and unimportant, okay? So I have no way of finding out. But I know what is good for me. The file system says, I have various pointers. I will keep my pointers or the auxiliary information or the metadata consistent so that I am sane. It's tough that you lost something, okay? But as long as at least I am sane, at least my pointers, etc., are in reasonable condition, most of them, I am still able to service rest of you, right? So that's what the file system does, okay? That's the reason why, unless you take special care, a file system can lose certain things, whereas a database will do the opposite. Will try to keep, because usually databases is used for some, let us say, inventory, some finance packages, various things like that, where money, real world things are there. Whereas a file system can also be as accurate as a database if it wants to be, but general design point for a file system is to make sure the metadata is completely intact, okay, at the cost of losing a few sectors here and there. If you lose a few sectors here and there and you lose some pointers, you do FSCK, file system check, and it will basically recover whatever can be recovered and then it gives it to you. It will, at the end of it, the file system says, I am sane. Some garbage happened, some bad things happened, some sectors got lost, some got corrupted. At the end of it, I am sane, I can still use whatever information I could legitimately pick up from there. I still will put in a reasonable format, I'll give it to you again. Okay. So there's a different kinds of models about how to handle loss. Okay. And there are many other parts. I'm just giving you 2 examples. You can have many other styles of handling loss. Okay. So these are all again connection with naming and storing. You can start seeing now that these are all, because you asked to retrieve something got lost. What do you have to do? That all these things are connected with that. Okay. Again, if you are asking for storing and retrieving stuff, it turns out there are device specific aspects, okay, that determine speed. Okay. For example, tapes have a certain notion that you have to read and write sequentially, whereas discs, for example, they can be more random access. Okay, so these things actually determine a lot of the effective speed at which you get things. Sometimes reads can be sequential, it can be non-sequential, it can be random. Okay, what is an example of a sequential thing? A good example is you are watching a video movie. Most likely video is sequentially encoded, so just keep reading it one at a time, systematically read it. For 2 hours you will be doing it, okay, mostly. Okay, it can be non-sequential. What's a good example of a non-sequential one? Suppose you are let us say looking up some address book, whatever, right? Depending on the search string, you will find it will be in different parts of the storage system. Okay, it can also be random. Okay, you are updating let us say some information structure with new information is coming in, it is being stored at different places. So it's making seek here, it's seeking there, it is seeking there, it's writing it here and there. Okay, or your information retrieval system, people are asking different types of information. Some guy could be asking something on how does let us say how does one plant grow. Somebody is asking how does if a child has fever, what has to be done, various things of that kind, right? So these are disparate types of information that are stored different places, and it could be on the disk at different places. So you can be seeking randomly. Okay, now it turns out that the most successful storage device so far since the last 60 years or so has been the disk. Okay, the disk was introduced first in 1956, and it's still today the most important storage device. Okay, so this is an electromechanical contraption. It has got, let us say, some mechanical components and some electrical components. Okay, what are the mechanical components? It's got a head which is rotating. Okay, and it will, sorry, the spindle is rotating and the head also can move. Okay, okay. So there is a mechanical aspect to this. Okay, the rotation of the spindle and that of the head also. In addition, what can also happen is that when for power management, you may want to stop the spinning. When you're stopping the spinning, you have to, the head also has to be put in a safe place. If you don't put in safe, it goes and sticks into the surface. Okay, you might lose some bits. Okay, so there are some aspects that are very peculiar to disks because of the electromechanical aspect. Okay, so you will find that you cannot drop a disk. If you drop a disk, most likely there can be some serious problems. Or you cannot use the disk in Tibet, for example. Why can't you use the disk in Tibet? Because it turns out in Tibet the air is so thin, okay, you don't get the kind of, let's say, Bernoulli effect that you get in when you are here. So don't take your laptop to Tibet and expect the laptop to work. It won't work. Okay, you need to do something else. Okay, probably not. You need to use solid state devices. Okay, so there are a lot of device specific aspects like this. Okay, and so unless you are clear about these things, your system will not perform well. Okay. The other aspect is writes in place or out of place. If you look at a tape, for example, what is the, suppose you have some piece of information, you want to update it, right? So normally what will happen is that you will take the piece of information, read out, modify it in memory, then you write it back. Okay. Now there are two possibilities. I can write it back where it was, or I can write it somewhere else. Okay. Now what people figured out in the tape kind of systems was that you read from one read tape and you write on the write tape. That means you read something from here and then write on this one. So this is an example of where writes are not in place. That is, you are updating something, but you don't update in the same place because writing onto a different tape. Okay. Now a disk actually did, it turned out the disk slightly altered the situation a bit, where in-place updates became slightly more easier. Okay, so because disk made the writes in place a bit more easier, most file systems started using that. But nowadays there is a new type of device called solid state disk, flash devices, where again it turns out it is more easier to write out of place than to write in place. Reason being, in a solid state disk you have what is called a read size, a write size, and also what is called an erase size. Now in these devices you will find that the read size might be something like 4K, write size may be 32K, and the erase size might be 2 megabytes. What is the issue with this kind of devices? It turns out in these devices, if you write, you will have to erase it before you can complete erase it. That means that's a separate operation called erase has to be done before you can write to the same place. Okay. So in a sense, erase makes that particular area of where you are writing completely clean in some sense, then only you can write again. Okay. So now it turns out that the write size is let us say 32 kilobytes. So if you write here, but the erase size is this big. That means if you want to write 32 kilobytes and you write again the same place, that means you have to erase 2 megabytes, because the size is determined by the technology, which is 2 megabytes. So it does not make much sense. So what you would actually like to do is, it is written here previously 32 kilobytes, you write to some other place, just like the tape, okay, write to some other place, and then once this use of this particular area is finished, completed, you release it as free area which can be used again, reused again. Then you do the complete erase. Okay. So there are these kind of issues also are cropping up now. That's why you will notice that if you have a mobile phone, it will have some new types of storage devices. Most of them have this flash kind of characteristic, and there is some special logic so that all this can be done effectively. Okay. So I just wanted to show that this naming and storing is non-trivial. There can be unusual complications because of various aspects, starting from basic aspects. I told you from lambda calculus what it means, but these are the two powerful operations. Okay. Starting from there, you can see the kind of computers that are required, the issues around metadata, about the device specific aspects, all these things are involved. Okay. So now again, let's you also need to think about large persistent data structures. What are these things? I think I mentioned to you earlier that you use devices like disk and storage, disk and tape for example. They are persistent structures. What does persistence means? Even if you remove the power, it remains. Whereas if you look at DRAM or DDR kind of memory, all those things, if you remove power, that data disappears, right? Now, unfortunately for us, the tape and disk are very slow. Even SSDs are slow compared to memory, okay? And you can't really do, CPU cannot directly access them, okay? So that means that whatever data you want to manipulate, it has to come to memory first. That means there are two copies available, okay? One is in the storage medium, one is in memory. Now there is, once you have two copies, then there is an issue of consistency. How do you ensure that if something is there in memory and you expected it to be the same value in the storage also, somebody has to make it happen. It won't happen by itself, okay? Either you do it through hardware, which is not usually done. You want to give some flexibility so that if it is done in hardware, then there is no point in having two copies, okay? Because you can as well work with one, okay? So normally you keep a copy in memory for as long as it is safe. When you want to make it persist, you put it in the disk or tape, okay? So there is some kind of judgment you want to exercise when you want to move across these two areas, whether to go from disk to memory, memory to disk, okay? So there are also issues called atomicity issues. If I am, there's a large piece of data, I can not write it in full one big section, Okay, I cannot write a 4 gigabytes in one shot atomically. That means without any intervening operation. I write this, some part. In principle, somebody else can also execute after I finish this part. I want to write this much, but I written only this much. Somebody else can come in and interfere with what I am doing. Okay. So I have to figure out how to avoid atomicity issues also. Okay. How to ensure that I intend to write this big, and logically it should look as though I wrote this big. Okay. Without, in spite of whatever other operation other people are doing. Okay. So, there is a big issue of atomicity and consistency. This is also a very big, fairly big subject, large subject which we need to look into. And since we are talking about large scale systems, right, we need to also worry about algorithmic aspects. Your terabyte system, for example, is really large. I think you may be surprised to know that if you think about how much data you might be inputting yourself, what is the typical writing speed of a person? It will be about 40 characters per minute, or okay, we will make it 100 characters per minute, right, or even 200 characters per minute, right. You think about it, how much can you write in 1 hour? 200 into 60, how much is that? It's about 12,000 characters. How much is that? It's 12 kilobytes, right. If you work for 1 hour consistent without taking a break, you are putting 12 kilobytes. If you multiply that by, let us say you work for 20 hours, let us say. So how much is that? 12 into 20, 240 kilobytes. You basically barely got to 1/4 of a megabyte. Even if assume that you work continuously for 1 year without break, 1/4 of a megabyte into 360, you basically got to 90 megabytes, right. So 1 full year you barely could, without taking a break, you have essentially 90 megabytes you can input. That's all, nothing more than that. Okay. And even if you work for 10 years, it will be 900 megabytes, about 1 gigabyte. A terabyte is how much? 1000 gigabytes. That is 0.1% of what you can do. Okay. So your terabyte is about 1000 times than what you can do in 10 years if you didn't take any break. Okay. So these things, basically what I am trying to say is that your ability to deal with this scale of systems that we talk about at a human level is no longer feasible. Okay. What is happening is that you are generating small amounts of information, but we have programs which are generating lots of objects. In a sense, what you are doing is you set in motion certain things which creates a lot of other objects. Okay. And that is basically where all this large number is showing up. By ourselves we are not able to do it. Okay. So what is happening now is that the scale at which you are operating has suddenly changed. Okay. So the size of object can be in gigabytes, the number of objects can be in terms of hundreds of millions. Okay, it's possible. Okay. So because of this size at which the things are happening, you need to find better ways of storing and accessing things. Last class I mentioned about mail directories. They can have thousands of messages. I mentioned that my own directory which I keep in IMAP directories, it is about 18,000. Today I checked it, it's 18,000. Okay. So 18,000 files sitting in a single directory. Okay. When you are searching for these things, you cannot use any order of n square algorithms. You need to use hopefully better algorithms. That means that you have 17,000 entries or 18,000. You need to keep some fast structures for accessing it. What's a good example of fast structure? Probably hashing schemes. Okay. And notice that this hashing scheme has to change every time I add or delete things. Every time I delete a message or every time I add a message, I actually have to update this hashing scheme also. That has to be also be very fast. Okay. So, and there is a lot of complexity in some of these things. Okay. The reason why certain systems, when you use it for the first time, it works very well, but after some period of time, it tends to be becoming slower and slower and slower. Okay. I think some of you must experience this. Okay, it's because it may be operating very well when the scale is small. Once you cross a certain scale, it may no longer work very well. And it can also happen in very devious ways. For example, suppose I have a system which has got 16 gigabytes of memory, okay, and somebody is keeping this metadata somewhere, right? The operating system says that I have 16 gigabytes of memory. It is some piece of information somewhere sitting there, right? It has to know how much memory is there, otherwise it can't manage the memory. Let us say by bad luck, the 16 is represented in binary as 0, 1, 0, 0 something like that, right? 16 gigabytes, it has got some ones and zeros, okay. Okay, I shouldn't take 16 gigabytes, let's take something like 24 gigabytes, okay. Then it will have some 1, 1 something, right, because it's 16 plus 8. So you will see the representation of 24 gigabytes, there will be 1 and followed by 1, followed by so many zeros. Now let's say by sheer bad luck, okay, that 1 got flipped into 0. So you thought you had 24 gigabytes of memory. It may now happen that the operating system, if you don't have ECC memory or error correcting codes, it now thinks it has got 16 gigabytes of memory or could be 8 gigabytes of memory, depending on where it got flipped. So suddenly the system, what was working very well once upon a time, is no longer working that fast, because it's now doing a lot more thrashing, it might be moving things around, etc. Okay. The same thing can also happen in logical systems. That's why when you are thinking of this kind of scale like this happening, there are lots of auxiliary structures you keep. There is nothing which says that the auxiliary structures cannot get corrupted. And that's one of the reasons why often you will see some people say the database got corrupted. Okay, you are using, for example, Firefox, it is keeping track of some information about your browsing history, and it is using a small database, SQL database something, no, what is it, SQLite, and that particular database can get corrupted. When that gets corrupted, you will find that your Firefox is no longer working, okay. Basically some critical piece of information it was using, basically it's some metadata about how to access whatever history that we had. That SQLite is essentially keeping that metadata. That got corrupted, and now no longer you can access anything, okay. You get into some messy situation, and usual solution is saying that you delete that some file, okay, the database file, and it will automatically re-index it again, and you will get a new thing, okay. So all these things keep happening. So if you are talking about these large scale systems, you will have a lot of auxiliary structures to speed up things, but you also have to be worried about what will happen to those things if they get corrupted, okay. That's something you have to worry about, okay. In addition, there are concurrency issues, okay. If you create a file, you need to lock the directory. Why is that? Because you have a directory and you are adding something to it, right. You want to add something to it, you may want to update some structures. I told you something about hashing structures so that you can look up fast, or even just simple fact that previously I had 999 files, now I have 1000 files. I want to update it, right. But if I want to update it, if there are concurrent operations, what will happen? I need to make sure that the concurrent update goes through right. I think some of you have done operating systems courses, you will notice that this concurrent operation has to be done properly, you have to take locking. So the way it is done is, you have to lock the directory, okay. Now if you lock this directory, it can create some other interesting complications elsewhere, okay. So it turns out that this directory, if it becomes lock bound, then other parties cannot update that same directory. They might see some latencies, but sometimes this kind of effects, they can travel upwards also, okay. What I mean is saying is that I want to access something, this guy is locked it, some other operation wants to access this, and there is a subsidiary operation that needs to lock the directory itself, okay. That means that this guy is waiting for this directory, and this guy's already locked this directory previously, okay, and so some other operation might require that other the directory on top, okay. So basically all these guys upstairs, they're all waiting for this guy to finish, okay. So it can go all the way to the root and the whole system can hang. Again, some of you might have noticed that your Linux system sometimes hangs, sometimes it just seems to be idle and suddenly moves with a jerk, right. Some of it could be some of these locking kind of issues. In large scale system, you have to worry about this. And that's why it's really magic, to me at least. You go to your favorite web browser, you type some few keywords, and the Google system will give you an instantaneous answer almost. The question is, how does it do it, right? It's something truly amazing, right? Basically, it can give you, it is searching something, I don't know where it's keeping the information, it's probably keeping something in Australia, and probably, who knows, Malaysia or Japan or somewhere in here, there. I type something here, it is going through these networks, it's going through the storage systems, it is able to figure out, and it is searching and giving the information in fractions of a second, okay. The question is, how can you engineer systems so that in spite of whatever problems I am talking about, it can still do a proper job, okay. That is where the challenge is, okay. Of course, the standard solution for all these things is try to make sure that almost everything that you are using is in memory, okay. What you do is you keep all the metadata in memory only. Don't let it keep it in disk. So the metadata is the thing which tells you how to look and get more detailed information about something. If it is in memory already, then you are not wasting time trying to access from the disk itself, okay. So you already, the first part of your access already is very fast, and then if you get accurate information, you are able to, if you do some further caching and other kinds of things, you might be able to get things very quickly, okay. So anyway, this is something I wanted to think about, because these things, the reason why these systems are so tricky to design is because you have to think about all these things, okay. And so I was mentioning algorithm aspect needs to be carefully taken care of, and this is critical with web level storage systems, okay. Basically this on a large scale, you have to figure out how to do this incorrectly, okay. And because of this, it turns out that many newer models have come up, what are called key value stores. They are slightly more flat systems compared to file systems. File systems give you a lot of functionality because applications use it. They require lots of support, applications require a lot of support, and the file systems have been developed since the 1970s. The kind of file systems we use, the history started about mid 1965, okay. Basically our original Unix, right, the original file system that came with Unix is what roughly we are still using approximately, okay. And we have kept adding certain new facilities because we program in mostly C now, C, and most of the kernel code or the application code is mostly in C. So it has got a certain idea about how to request storage services, and mostly all this, the same thing that was there is mostly still there with some additional newer facilities, okay. But with the web kind of systems, our access patterns are different. We are accessing it mostly in different types of applications, for example, the search kind of applications or the Facebook kind of applications. It requires a slightly different model, and key value stores are better for it. You don't need the kind of things that we need in the case of file systems. A good example is if you use some storage system on a particular machine, right? Let's say you have a PC, you have a file system running on it. The file system is going to do things like caching for you. It's going to do some, if I have already referred to that file once before, I can, the next time I refer to it, I refer to the handle, I don't refer to the full file name, okay. Now, this kind of facilities are there in file systems, okay. Now, on the web kind of systems, such facilities may not be that critical, okay. So, you can still refer to it using, without using, you can give it still the same name that you used before. You don't have to find a file handle, for example, okay. So, it turns out that key value stores, they optimize in a different direction, okay. So, those things have become common, okay. Again, we will look into this, some of this next time, okay. Okay, let us just Again, we'll go into some of the details later, but this is an example of the kind of metadata that is kept in a file system. This is the ext2 file system that is there in Linux systems. To keep some information about some piece of data, the metadata that is corresponding to that file is called inode. This is inode. Okay. It has some information about the file. For example, the size of the file, when was it created, when was it last modified, all this stuff is here. Okay. This is the file information. And it also has the data also. Okay. That is basically the blocks of information. So, the first 4 kilobytes, the pointer to it is here of the data. The second 4 kilobytes is here. Okay. Now, typically we have about 7, 8, 9 of this what are called direct blocks. Okay. But it turns out that if you use direct blocks all through, then basically you need, if you have something like 100 megabytes, right, you need so many entries here, 100 megabytes. It does not make much sense. So, they use something called indirect blocks. What they do is, I have an indirect block here, and this itself again in turn stores the block addresses. Okay. So, this is the first level of indirect blocks. So, this is not storing the blocks directly now, the address of blocks. You have to go to another auxiliary structure, and this itself now actually talks to the blocks. So, normally essentially what is happening is that you are able to access about 7 into 4K or 8 into 4K directly, about 32 kilobytes or 28 kilobytes directly. Then this will give you access to, if it is this itself is 4 kilobytes, you are talking about 1000 addresses here. So, 1000 into 4 kilobytes, 4 megabytes here. Now, we are able to go from about 28 kilobytes, we now got to about 4 megabytes. Now, 4 megabytes is still small. So, basically you will have one more level of single indirect block, these are double indirect blocks. Okay. You will now go to up to gigabytes. Now, gigabytes are still not enough. So, you will go to triple indirect. Okay. People have gone up to triple indirect, but people are not doing anything beyond that. Okay. That is the reason for it. What is the problem with this kind of structure? You will find that the structure is slightly regular fine. Okay. There is direct blocks, after some time it is indirect block, after some time you get indirect. But you notice that to access triply indirected blocks, first I have to access the first level indirect block, then the second indirect block, third indirect block, then only I can get a block. Why is it a problem? There could be a problem because suppose I am doing multimedia. Okay. In multimedia, I need to get access to blocks within certain bounds. Now, basically what I am doing right now is that I am telling you right now, if I have this kind of structure, I might be 4 times as slow as when I am accessing something here than when I am here. That means your design has to worry about the variation at this level, and multimedia files, audio especially, you can't tolerate too much jitter. Okay, you need to get small amounts fine. In the audio file, it turns out you just need typically about hundreds of bytes, this when I am speaking for example, or music, typically a small amounts of bytes, okay, but I need it every 10 milliseconds, and that is very strict. Okay. So, if I go to 4 levels of indirect, you know that access to a disk block can take about 10 milliseconds. So, I have 4 of those guys, that means I can take as much as 40 milliseconds. So, I cannot handle audio kind of stuff. Okay, it does not work. So, this kind of design is the older design. It has stood well as long as our file sizes were small or we did not use multimedia files. We did not have multimedia playback, okay, like audio and to some extent video. Okay. So, that is why nowadays people want structures which are more symmetric. Okay. Symmetric in the sense that whatever block you are referring to, it should take the same amount of time, approximately. That is why you have something called B trees, B plus trees, those kind of things are used in more newer types of file systems. Okay. I think I will conclude at this point. In next class, we will look at some slightly different types of systems at a slightly bigger scale like the Google file system. We just give a high level perspective and continue from there. Okay. Thank you.